Hi everyone, let's talk about a puzzle called Mountain Trip. In this puzzle we're going to have to do a bit of reading. There is a mountain that has a well-defined path from a point at the bottom of the mountain, a particular point, all the way to the summit, so at the top of the mountain. On day 1, a mountaineer begins at the bottom point of the path at 6 a.m. and climbs the path until she reaches the summit, so the top point, at 6 p.m. On the second day, the mountaineer begins at the summit at 6 a.m. and reaches the bottom point at 6 p.m. Now, there are a few conditions, or rather lack of conditions, that I want to mention about these two trips, the uphill trip and the downhill trip. First of all, the mountaineer might have different paces at different times, so the mountaineer doesn't have to go at the same speed at all times, which makes sense. This isn't necessarily a completely theoretical scenario where the mountaineer is always traveling at the same speed. And secondly, the mountaineer might sometimes stand still. Maybe she's tired, and sometimes she might go backwards, maybe because she wants to check out something that she passed by earlier. And finally, the downhill and uphill trips are not necessarily reverses of each other, so they could be totally different. So we only have the conditions that we stated so far. And what you want to prove in this puzzle is that regardless of all these lack of conditions, that there exists a point in time between 6 a.m. and 6 p.m. at which the mountaineer is at exactly the same spot on the path on both days. So I'll wait for 5 seconds. You can think about this, pause the video, and then I'll cover the solution. 5, 4, 3, 2, 1. All right, let's take a look at the solution. First, we're going to cover an intuitive solution, so without any fancy math. So on the second day, when the mountaineer is going down the mountain, what you want to do is get another mountaineer to go up the mountain in exactly the same way that the first mountaineer did on the first day. And you can tell intuitively that sooner or later the two mountaineers will collide. So that is the point in the path and the time of the day at which they will intersect. Now, next what we're going to do is cover a rigorous solution, and we're going to do this using the intermediate value theorem from calculus. What we're going to do is associate the physical path, which is a continuous curve, with the closed interval from 0 to 1, so that at any point between 0 and 1, that point is how far you've gone into the path, or the fraction of the path you've gone into. And so 0 is the bottom of the path and 1 is the summit. And we'll make that the y-axis because we want the x-axis, which is time, to be the independent variable. And the x-axis will also go from 0 to 1, where 0 is 6 a.m. and 1 is 6 p.m. Now, the uphill function has f of 0 equal to 0 and f of 1 equal to 1, and the downhill function has g of 0 equal to 1 and g of 1 equal to 0. You can tell like one is going uphill and the other one's going downhill. That's why we have these properties. And what we want to prove is that these functions intersect at some point in time. And we can do this by subtracting g from f. So you get f of f minus g of 0 is equal to negative 1. And you get f minus g of 1 equals to 1. And so there has to be some point in the interval from the open interval from 0 to 1 by the intermediate value theorem, such that there's a root of f minus g, which means at that point from 0 to 1 open, there is going to be there's a point where f of r equals g of r, and that's the point in time at which there is a collision of the two paths. So that means that's the point where the same point in the path is reached at the same point in time on both days. Thanks for watching, and I'll see you next time.